Introduction to limits. Goals here: understand the concept of a limit and be able to find a function's limit using a graph and a table. We'll see how both of those work. Understand the limit notation. There's going to be a lot of notation for limits. You need to understand what it indicates, what it means, and then be able to find one-sided limits and see how they relate to the two-sided limit that we basically will be starting with. So why are limits important in calculus? Why are we looking at them at all? Well, they are a key concept in the development of derivatives and integrals. And derivatives and integrals are like the two fundamental topics that you're going to see in the calculus course sequence. So can't have calculus without derivatives and integrals, can't have those without limits. So without limits, calculus as you know it would not exist. That's why they're so important. So what is a limit? Well, the basic idea is to let a variable's value approach a certain numerical value, but not equal it. So we're going to get really close to a number, but not equal it. So for example, if we're finding the limit as we approach 4, the idea of approaching that 4, we're going to come in from the left side of the number line and look at like 3.9999999999999, or coming in from the right side of the number line, we get to like 4.00000, and infinite zeros, and then 1. So we're not actually going to equal the 4, but we're going to get really close to it without touching it. So how does that work in functions, which is what we're going to work with a lot when we're finding limits? Well, domain value in your classic f of x, the x value, will approach a certain value. So we're going to let the x, the domain, approach a certain value. And then we're going to look at the corresponding range value, the f of x, the y. And we're going to see that that is going to be approaching something. And whatever that value is that the function is approaching as our domain is getting close to something will be the function's limit value. So what does this mean? How do we do this in a picture? So let's take a look at this in a little graph here. So for this example, just pick this function, this f of x with the x cubed plus 3x squared minus x minus 1. And I'm going to go ahead and find the limit of f of x as x approaches, this is why you're really going to appreciate the notation later on, so as x approaches -1. So I'm going to first come over to the x-axis and put the -1 right there. So I want to find the limit of the function as we approach that -1 on the x-axis. And then what we're going to do, we're not going to start way over on the left, but I am going to come in from the left side, the negative side of the x-axis. And as I get close to that -1, I'm going to start looking at my function values and be like, where am I getting close to here? It looks like I'm getting close to that one there. And then I'm going to do the same thing from the right side, the positive side of the x-axis. And again, I'm going to start as I get a little closer to that -1. And as I go up there, looks like I'm also approaching the same value. And the limit then of this function as x approaches -1 is going to be 2. The y value is 2 as my x gets close to -1. So that would be graphically how we could do it. And let's take a look at how we could do this in a table. So in a table, we're going to have to start with some x values, and I'm going to come in from the left side and the right side again and get close to that -1. So I'm going to go ahead and fill in some values on this table for the x's. And what you can see here, starting at the top of the table, I'm at -1.1, which means I'm just 1/10 to the left of -1 on that x-axis. And at the bottom of the table, I'm starting at negative 0.9, which is just to the right of that negative 1 on the x-axis. And I'm working my way in closer and closer until I get to right here. In between those two values would be the negative 1. So from the left side, start negative 1.1, and I get up to where I'm basically 100,000th away on the left side. And same thing on the right. I come in from negative 0.9 and just getting closer and closer till I'm like 100,000th away on the right side. And then what you do with these values is you plug them into the function and see what the y values are and see if there's a pattern that develops that will indicate a good guess for the limit. So let's go ahead and fill in those function values there. And after you fill in the function values, you start looking at the pattern that develops as you come in from the left side. So starting at that negative 1.1, working your way down until you get to that, close to that negative 1, and then working your way back up from the right side until you get, again, close to that negative 1. And you could be saying to yourself, why didn't you just plug in negative 1? You would get a value. And that'd be great if we wanted f of negative 1, but I want the limit as x approaches negative 1, so I don't get to plug in that negative 1 at this point. I don't get to do that. I just can get really close to it. So I look at my function values, coming in from the top down, the function values, I start like that 2.399, and then I start getting closer and closer, it looks like, maybe to 2. And then from the bottom of the list, 1.601, working my way up, and I'm also getting close to 2. So in that table, we would use the table to guess that the limit is 2. And that is verified by what we saw in the graph. And it's just a different way of looking at limit values of functions. So we can do a graph, we can do a table, and up here in the graph, when I wrote this out on the right side here, when I wanted to indicate what we were doing with the limit, that's a lot to write, and mathematicians don't like to write that much. So let's take a look at the notation that will make this whole thing I wrote here in that box a lot smaller. So the limit notation then for limits of functions is going to be the limit, or we're going to abbreviate that even down to LIM. So when you see LIM, that means limit. Underneath, we're going to put X with an arrow and then A, and that's the X approaches a certain value part of the notation. If we were looking at the last example, I would have that A being a negative 1. And then we're going to let everyone know what function it is we're taking the limit of, in this case, the f of x. And then if it exists, that limit exists, we're going to say that it equals L. So we have the limit of f of x as x approaches A is L. And that's how it reads. Again, the limit of f of x as x approaches A is L. Sometimes you will hear me, or you may say that in a slightly different order. The limit as x approaches A of f of x is L, tomato, tomato. But the important thing is you're saying you're doing a limit. What is the x approaching? What is the function? What is the value? All those things are in there. And again, the key idea is that x gets close to A, but never actually equals A. So what we've seen here in this notation is really a two-sided limit. You're coming in from the left, coming in from the right, looking at what the function value is, and that ends up being the limit. Well, what if you had something like this? If this was your function graph, and if I wanted to find, in this case, the limit as x approaches 1 of f of x. So now I come down here to my x-axis, I put the 1 that I'm going to approach on the x-axis, and I start looking at the y values. So coming in from the left side, the negative side, and we get up here and we get, looks like we're going to get close to that value of 2. Then I come in from the right side, the positive side, and as I move the graph, getting closer to the x value of 1, I see that my y value is getting to 4. And this is a problem. I got a 2 on one side, a 4 on the other. What does that mean for the limit as x approaches 1 from both sides? Well, in short, it means it doesn't exist, but we do have a left side and a right side limit that do exist. So this is where the one-sided limits come in and allow us to kind of differentiate between what's happening on the left and the right in graphs like this or in functions like that. So the notation then for the one-sided limits is going to be as follows. We'll look at the left hand first. And notice that it is very similar to the two-sided limit. The only difference in the notation is right here in the superscript. Above that A, in that x approaches A part of the notation, you put a negative sign in the superscript, and that tells you that you're coming in from the negative side of the x-axis, from the left side of the x-axis, and then going over until you get close to that A value. So left hand, you use a negative in the superscript of that notation. So for the right hand, you might be able to guess what this would be. I'm going to go ahead and write it here. And the only difference for the right hand is that your superscript is now a positive, telling you you're coming in from the positive side of the x-axis and moving your way in until you get close to that target value of A. So left hand limit, you have that negative, you're coming in from the negative side, the left side of the x-axis. Right hand limit, coming in from the positive side, the right side of the x-axis to get close to that A. So up above here, we would be able to say that the left hand limit was 2, the right hand limit was 4 in that graphical example as we approach that 1. So in general then, we have left and right, and sometimes they're going to be equal. In this case, they were not in this example with that broken graph. So in general, the left and right hand limits must be equal in order for the two-sided limit, the x approaches A without the superscript, to exist. So let's see this in fancy notation. And what you see here is left side, you got this limit as x approaches A of f of x equals L. Double arrow there means if and only if. It's basically if then in both directions. So we would say if this left side of the arrow is true, then the right side is true. And also, if the right side of the arrow is true, then the left side is true. So that's the if and only if. It's a double implication. One side implies the other and vice versa. So if the left side, this limit as x approaches A of f of x equals L, then both the one-sided limits, the left-hand limit and the right-hand limit, must also equal the same L. So we would say here also, if and only if can be written as IFF. So what you have is you got to have the left and the right being the same value in order for the two-sided limit to exist. That means up above we have a left limit of 2, a right limit of 4. Those both exist, but the two-sided limit would not exist. So you just say limit as x approaches 1 of f of x does not exist, even though the limit as x approaches 1 from the left of f of x equals 2, and the limit as x approaches 1 from the positive side of f of x equals 4. Okay, so that's your basic introduction to limits. You've got the two-sided limit, you've got the one-sided limits, and the relationship between them. The one-sided's got to equal the same thing for the two-sided to exist, and we'll see more of this as we move forward. Thank you for watching.